In this video, we'll be describing the shapes of various molecules using what's called valence shell electron pair repulsion theory, or Vsepr theory. In order to understand the shapes of various molecules that may appear to have the same formulas, we need to know something about how the pairs of electrons are arranged around the central atom. So, for example, we can compare two molecules such as boron trifluoride and phosphorus trifluoride. One might think that they adopt the same structure because they have the same basic formula in which there's a central atom and three atoms attached to it, but in fact they adopt quite different structures. Boron trifluoride adopts a structure in which the boron is in the middle of an equilateral triangle, essentially forming a bond angle of 120 degrees between the fluorine, the boron, and another fluorine. Whereas phosphorus trifluoride adopts a trigonal pyramidal structure in which the phosphorus sits on top of that equilateral triangle. The bond angles in this case, the fluorine, phosphorus, fluorine bond angles are approximately 90 degrees. In order to understand the molecular geometry or the arrangement of the atoms within a particular molecule, we need to understand something about how the molecular geometry is determined, and this is a result of both the bond distances between the various atoms and then also the bond angles, which is defined by three different atoms, and then also the presence of any non-bonding or lone pairs of electrons that may also occupy space. As an example of how one might go about determining the molecular shapes of a particular molecule, we can look at carbon tetrachloride. This has got a formula of 1 carbon and 4 chlorines. The carbon is the central atom, and the chlorine atoms are all bonded to it. In this particular case, then, the distance between the carbon and the chlorine is approximately 1.78 angstroms, and the chlorine-carbon-chlorine angles are all equal, and they're all about 109 degrees. This basic shape associated with this particular molecule is known as a tetrahedron. The tetrahedron is defined by the fact that there are 4 triangular faces to this geometric figure, essentially bringing together 4 equilateral triangles to form the three-dimensional shape. We will be using valence shell electron pair repulsion theory or in other words Vsepr theory, to predict the shapes of our molecules. It turns out that the premise here is that pairs of electrons which have negative charges are going to try to repel one another, and the goal is to get these pairs of electrons as far away from one another as possible. Turns out that the regions that the electron pairs can occupy also then correspond to certain geometric shapes. We need to take into account not only bonding pairs, but also the so-called lone pairs of electrons. We are also going to have to recognize that the regions of space that are occupied by a single bond are going to be the same regions of space that might be occupied by a double bond or a triple bond as well. And so the Vsepr theory does not make a distinction between the bond order and the region of space, and you'll see this as we do some examples. So the first thing that we need to consider is what are the electron geometries, the regions of space that define the geometric shapes, and this is all determined by electron pairs. So if we have two electron pairs, in order surrounding a central atom, the structure will produce a angle of 180 degrees between the two pairs of electrons. And so in this case, this would be referred to as a linear structure. If we have three pairs of electrons, or three regions of electrons, this would be a angle of 120 degrees. This goes to the corners of the equilateral triangle. And so the angle here is 120 degrees. And if there are four regions or four electron pairs, the optimal angle is 109.5 degrees. So the so-called tetrahedral shape. There are two additional structures that we need to consider. These are for Lewis dot structures in which the central atom can violate the octet rule. And so if there turns out to be 5 electron regions or electron pairs around a central atom, this will correspond to what we refer to as a trigonal bipyramid. This is a combination of an equilateral triangle and then having two pyramids sitting right on top of one another. And so in fact there turns out to be two different kinds of angles in this structure. There are the 120 degree angles that are part of the equilateral triangle, and then there are 90 degree angles that occur between the so-called axial positions and then those triangles. In addition to that, it's possible to have 6 electron regions. This goes to the corners of the so-called octahedron, and in this case, all of the angles are 90 degrees. In order to predict the molecular geometry, we need to follow the following steps. In the first case, we need to be able to draw the Lewis dot structure. Once we have determined Lewis dot structure, we need to count the total number of bonding regions and then also the number of lone pairs around the central atom. Remembering that bonding regions are any kind of single, double, or triple bond. They are all counted as one region. And then we're going to arrange those bonding regions around the central atom along with any lone pairs in one of the standard geometries that we just discussed. As a simple example, we're going to start out with beryllium dihydride. In this particular case, we draw the Lewis dot structure for beryllium dihydride. It happens to be one of the exceptions to the octet rule. So in this particular case, the Lewis dot structure has 2 regions around the central atom, which is the beryllium. And so hence this corresponds to the linear structure as shown here, in which there's a 180 degree angle between the 2 bonding electron regions. In the case of then that geometry, we then have to recognize that those 2 pairs of electrons correspond to the bonds to the hydrogen atoms. And so in this case then the molecular geometry corresponds to a molecular geometry that we would call linear. As an example of linear structures, the beryllium difluoride is a good example of a linear structure. In this case, the central atom beryllium only has 2 electron regions around it, both of them being bonding regions. There are lone pairs in this molecule, but they are on the fluorine, and it's only the central atom that will be of concern to us in predicting the structure. In this case, those electron pairs that are bonding for beryllium will try to get as far away from one another as possible, so hence this adopts a linear structure and the bond angle will be at about 180 degrees. Another example of a linear molecule is when there's just one bonding region and no lone pairs. A good example of this is the elemental hydrogen, and so in this case there is no other possibility other than